us continue our discussion on distributed forces that we started in the previous lecture. So, just to remind you, so the question is that suppose you have a element of a truss or a beam such as what is shown here, and we want to know what are the forces acting on the support, and in this case the external force is distributed over the entire length of the force. So, we want to know we want to replace that by a single force acting at some particular location, and the question is how to do that. So, let us start with the following examples. So, here is a case of the uniform beam. So, these little arrows, they represents the load per unit length. Now, given this length load that is distributed over a length L, now what is the equivalent force? So, what is this equivalent force means? It simply means that, so if you want to replace this uniform profile of load distributed load, then by a single load, a single equivalent force, they must have the total force must be same. This is the first general principle. Now, in order to do that, so then of course, in this particular situation, it is very easy to calculate the total force. So, if these little arrows represents load per unit length, and they are in this 2D example, they are, let us say, it's a 1D one dimensional example. So, this is distributed over a length L, then the total force must be the area of a rectangle whose one side is L and the other side is W, which is load per unit length. So, then the total force must be W times L. So, remember this W per unit length. So, so it is force per unit length times length. So, dimensionally it makes sense that W times L has a dimension of force, which represents the total force. Now, the question is that where is this force? You should put this force. Now, in order to determine that, the general principle is that the total moment generated or total torque produced by this force about certain given pivot point that you have selected must also be same for the case of this distributed force and the equivalent force. Now, in this case it is easy to see that just by symmetry, because everything is uniform, then this you should put this force just at the precisely at the middle of the beam. This is just by symmetry. Similarly, in this case, now let us take the second example where you have a linear profile starting with a 0 load. So, in this case again we can determine the total force easily from geometry. So, again we can use the same principle that the total force must be. So, if you have W per unit load, but now the W's are different, but you can still see that the total force must be the area under this curve. So, this area under this curve is a triangle. So, this represents a length L, and this is force per unit length. So, this area represents the total force, and this area is easy to calculate, is area of a triangle. So, this is half times the base times the height. So, this so the total force is half WL, where W is the load per unit length. However, in this case it is not so easy to obvious to see where is the line of action that where you is of the net force. Now, we can obviously have a slightly more complicated example where we can sort of have a linear profile, but starting from a non-zero load. Now, in this case again we want to, if you want to compute this total force, we can sort of use this geometrical strategy that this total force must be the area, because these arrows are load per unit length. times the total length, that will give you the total force. And in order to calculate that, you can simply divide. So, it is kind of combination of the previous two example. So, the area must be the area of this rectangle. So, let us say this is at the one end, let us call that, so let us say this is my x axis and this is my origin and this is L. So, at x equal to 0, the load per unit length is W1, and at x equal to L, the load per unit length is W2. Then this area under this curve, this straight line, is the area of this rectangle plus the area of this triangle. So, the area of the rectangle is W1 times L, and the area of the triangle is given by half into the height, which is W2 minus W1. So, this is W2 minus W1 times the base, which is L. Now, again, but where is the line of action? So, this is somewhat maybe not easy to show. So, in the previous case, I have shown you the answer. The line of action is passing through a point which is not at the middle point, because it is not at the middle point because the forces are not uniform, and the you can see that. So, this is at 2/3 distance from the one end, and why? So, this is slightly bigger than the middle, because does it make sense? So, this is again I must mention that whenever you are analyzing a mechanics problem, one question that you should keep on asking yourself is, does it make sense? So, in this case it makes sense because the loads, as you go further from the left end, the load per unit length increases. So, that means you expect that there are more end towards the right end. So, the line of action of the force should be biased towards the right end, and hence you see that the line of action is bigger than the middle point. Because of this, with this example, now in this case the line of action is not so easy, because if you look at only the rectangle, you expect the line of action passing through the middle point, whereas if you look at this triangle, you expect the line of action passing through the 2/3 distance. So, this is L by 2 or half L, this is 2/3 of L, and then if you combine them, it is not easy to see which is the how to get the line of action. So, then what we want to know is that how to handle any arbitrary force distribution or distributed profile in one dimension. So, this is a one dimensional problem such as this. So, this is a completely arbitrary function, some nonlinear. So, in those cases, how do you, what is the general physical principle? And so, the physical principle is the following. So, first, to get the total force, that is the equivalent force, which is the total force acting on the beam. So, this must be the equivalent force, must be the total force. So, this you get. So, if you consider a small element such as this highlighted region, yellow region as dx, then as I mentioned before, if you know this load per unit, the load profile, load external force per unit length, this is W, then W times dx is now your force acting on this particular area element. Then the total force is actually the area under this curve, and hence, so if you start from, this is your point 1, this is your point 2. So, then your total force must be, you can compute simply by adding vector addition. So, in this case all the forces in the same direction. So, this vector addition turns out to be simple scalar addition of the magnitude. So, this is dF, and you add dF for each little pieces, then you get the total force. So, this is, and I put the two end 1 and 2 to remind us that this beam is a finite length and you go from one end to the other end. The second principle is that the distributed the total moment. So, if you choose any particular pivot point, and if you calculate the total moment or total torque generated by this profile of external force, distributed force, they must be equal to, so that to the moment generated by the equivalent force, point force, that is F net. So, what is the moment generated? Suppose we want to compute the torque about this any point on the left end. So, let us call that origin, and this is our x axis. So, this is our pivot point. at the left end. Then and suppose the net the total force or F net is acting at a some point x l from the left end. Then the moment, as you can see, is, so we have generated by this force F net is about this point origin pivot point O must be F net times x l in one dimension, because the and this magnitude is going to be, you can find the magnitude from the right hand thumb rule, it is going inside the screen. And what is the total moment generated by this distributed force? So, this is so this much is the force acting. If you take a element which is at a distance x, then and at that at a distance x, if the load per unit length is w, which is in general some function of x, then w times dx is the df, and then the distance is x. So, the x times df, that gives you the torque by this particular generated by this particular piece, and then you can get, and the, as you can see that the torque generated by each of the different pieces at different parts of the beam all points in the same direction. So, you can simply add them in an algebraic way and then you get the total torque, and because this is a continuous function. So, this instead of summation we are going to use integration. So, this is the strategy. So, now once you know the F net from this first equation, and then you can use this second equation to compute the distance or the position of the line of action. So, let us take an example, work out through an example to understand. So, here is a question that there is a beam given which is supported at both ends. On the left hand ends, this is a pin joint, which means this is kind of fixed, and on the right hand end you have a roller. So, that means we are assuming, so these two supports has different shapes, different types of support. In this case, the no horizontal force, the only force must be in the vertical direction. So, determine the reactions at the supports A and B for the beam, and the external and this line represents the external load profile. So, this is given and this design is given. What are the, so the question asks what are the forces at the support A and B. So, let us first analyze this this in detail. So, first thing is that what are the direction of the forces at, suppose this is, so first is let us start with a coordinate system. So, let us say that we take the point A as the origin of our coordinate system, and this is x axis and this is y axis. Now, the nature of the support determines that in general, in this particular case, the force that are acting at this point has two components. Let us call that A x and let us call that A y. Whereas, at the end B, the only possible component is B y, and the external force are given. Now, the first is that you do not have to remember a very complicated formula, you just have to remember the simple physical principles. So, let us first write the force balance in the x direction. So, whole structure is in mechanical equilibrium. So, this equation represents the force balance in the x direction. Now, you can see that only horizontal force that is acting. Okay, so, let us one more thing before that. So, what is our system? So, let us say our system is the beam, that is the red block. Then what are the surrounding? So, the important thing in the surrounding is the support A and support B and the external forces profile load. Now, note that in this case, since nothing is mentioned, we are going to assume that the beam is massless. So, we are going to ignore the interaction between the beam with the earth. So, now the we write down the force balance equation. So, the first equation is in the x direction. Now, only possible force in this case, all the external loads are in the y direction. So, no component in x direction. So, this means that only horizontal force is Ax, and since the whole thing has to is motionless is static, that means the Ax must be 0. So, that means we have only two unknowns, one is Ay, other is By. So, these are the two unknowns. Then we can write the force balance equation in the y direction, and then what do we get if we write down the force balance equation in the y direction? We get that. So, what are the forces in the y direction acting on our system? So, one force is Ay, other force is By, and then there is this distributed force, and in our free body diagram. So, let us say this is my beam. So, then we have one end, this is Ay, other end which is By, and then we are going to sort of assume we are going to replace this entire distributed force by a single external force F, and this is our origin, and we are going to assume that the line of action of the force is situated at a distance x l from the left end or the support A. So, sorry. So, this is the situation. So, now this is kind of one equation. So, you have two unknowns. So, we need one more equation, and this third equation is going to be the sum over m a. So, m represents the total torque acting on our system, and I have put this suffix a to remind us that this torque is calculated around this pivot point A. So, this must be 0. Now, if this is 0, so let me redraw the picture. So, this is A y, this is B y, and this is some F, which is the equivalent, the total force acting on the total external force acting on the beam, and this is at distance x l. Now, if we want to calculate the moment, so about this point A, so A y does not contribute because its line of action is passing through the point A. F and B y will contribute because their line of actions are not passing through A. So, then the total torque given by F is F times x l, because this is from the by definition, and the torque given by B y is B y times L. So, this distance is L, and as you can see that if you apply right hand thumb rule, they are in the opposite direction. So, they are cancelling each other, and hence the total torque is 0. So, that is required for, so that ensures that the beam does not rotate. So, now you have two equations and two unknowns, and now you can compute this B y and B s. Now, note that this F and x l's are actually known because this external force is given. Unknowns are B y and A y. Okay. So, how do I get F? Now, there are, if I apply the definition that we just discussed, is then F is given by, and let us go from 0 to L. So, this is one end which is 0, x equal to 0. So, let me remind you that this is my 0 and this is my x axis. Now, there are two ways to do that. First way is to sort of easy way and a lengthy way. So, anyway, so the first thing is that we want to know the Wx. So, how do I get Wx? So, this is starting from 0 and is a linear, clearly a linear profile. So, and then So, it is better to sort of divide it into two pieces, one piece from 0 to L by 2 the midpoint and the other piece from L by 2 to L. So, this is clearly an equation of the form y equal to mx. So, you can see that, and the slope of this equation is from 0 to L by 2, this Wx is given by now. So, the slope is given by W naught divided by L by 2, so that is 2 W naught by L. So, W naught is load per unit length at x equal to L by 2. So, does it make sense? If you put x equal to 0, you get 0, and if you put x equal to L by 2, you get W naught. So, this is fine. Now, for the other case, for the second piece, that is from L by 2 to x less than L. So, this we can find out by sort of assuming that this Wx is of a straight line of the form mx plus c with two unknowns. Then we have two conditions, that at x equal to L by 2, then W is W naught, which is, that means m times L by 2 plus c is equal to W naught, and W at L, that the right hand end is 0, it is 0, load per unit length is 0, that means m times L plus c 0. So, this gives me c, which is minus ml, and then if you plug it back in this equation, first equation, then you get W naught is equal to minus m L by 2, because m L by 2 minus m L is minus m L by 2, that means m is 2 W naught by L with a negative sign. Does it make sense? It makes sense, because this part the slope is, you can clearly see that the slope is negative. So, we get we can check that the right hand side is negative. Then our equation is, now if you use this condition here, then we get C, we can write out. So, m times L, which is minus 2 omega naught plus 2 omega naught. So, then our profile is 2 omega naught 1 minus x by L, and we can verify that at x equal to L this is 0, and at x equal to L by 2 this is W naught. So, this is our Wx. So, now you can go a lengthy way and you can plug in these two equations and do the integration, or we can look at geometrically in a quicker way. As you can see that the total force is the area under this curve, and the area under this curve is nothing but the sum over area of this triangle and the sum over area of this triangle. So, the triangle on the left has an area which is half times the base, which is L by 2, times the height, which is W naught. Triangle on the right has an area half into base, again the length is L by 2 into height W naught. So, I get half into L by 2 times W naught. So, this must be the total force. Now, next task is to compute the total torque generated by this external profile. So, this total torque, so this is our one equation, important equation. So, next task is to calculate the total torque. So, let me again write down this picture. This is A, this is my beam. So, this is x axis, this is A, this force is acting at a distance x L, this is B. So, this length is L. So, the total torque, as you can see, that if I is x times df. So, if this distance is x, then this piece about this point A. So, let us say this force acting on this dx part of, so this is a length dx, a small slice dx, then the total force is df, and the dF generates a torque which is x times dF, which is Wx times dx. Now, this integral goes from x equal to 0 to x equal to L. So, this is the total torque by the external force. About the pivot point A. So, when you sort of write these answers to these kind of questions, you should always write these details. It is very important to write these details that will help you to make sure that your calculations is correct. It also helps you to remember the basic physical principles. So, this there is no way we have to do this integral. So, this integral again we divide into Wx has two pieces. So, we divide into two parts. So, the first part was 2 W naught x by L dx. So, this is equal to, so you can take 2 W naught by L outside, we have x square dx. So, integration will give us x cube by 3 and 0 to L by 2. So, that will give us L cube by 8 times 3. So, it is 1 by 24. So, that will give us W naught by L times, and so this L and there will be L cube. So, we will get an L square 1 by 2 by 24. So, this 2 coming from top, and 1 by 3 divided by 1 by 8 is 24 times L square. So, that will give us W naught L square by 2 by 24. Now, the other term, and in this case the first term has x dx, which will give you x square by 2. So, this is x square by 2, and L by 2 to L is the limit of the integration, and the second term has sort of 1 by L sitting outside, and then you have x square dx. So, which gives us x cube by 3 L by 2 to L. So, this will give us so this 2 will cancel, and then you have L square minus L square by 4, which is 3 by 4 L square, minus we have 1 by 3 L times L cube minus L cube by 8, which is 7 by 8 times L cube. And the second term is L will cancel and get an L square, which I am taking out. So, this is 3 by 4 minus we have 7 by 24. So, if I add these two pieces, we get the total M is W naught L square 2 by 24 plus 3 by 4 is 18 by 24 minus. So, yeah, so this is not 7 because there is a factor of 2, this 2 which was inside. So, this must be 2 into 7 because of this 2 it is inside. So, this must be 14 by 24, and this if you get simplify this, you will get 1 by 4. So, the total torque is not L square. So, then we can sort of look at our equation of torque balance. So, our equation for torque balance. So, you can now calculate this is our external total torque M A, and now we can sort of determine what is X L, because F times X L is equal to this must be the total torque acting on the system, which is 1 by 4 W naught L square. Now, F is we just computed here, F is 1 by 4 W naught times L. So, this is half 1 by 4. Yeah, so again I made a mistake here. So, in the previous slide, so it should be so 1 half. So, because there are 2 factors of 1 by 4, so if we add them, you get a half. Half L times W naught times X L is equal to 1 by 4 W naught L square. So, from here you get X L to be half L. So, does it make sense? So, you determine that you can replace this external force with a magnitude of force, total force, which is half times W naught times L, and this is acting at a distance precisely at the middle point. Does it make sense? Well, the line of action do make sense, because by symmetry you expect that if you take any force, then the line about the middle point, any part of the force distribution is sort of symmetric about the middle point. So, by symmetry we expect that the line of action of the force should go through the middle point, but you have to do this calculation to actually verify that. So, now we can determine the unknown forces B, Y, L, because we have calculated F and X L. So, what we have is 2 equations. Our first equation shows that from here, our first equation, let me write down the first equation again. So, from this equation we got that A y plus B y and minus F is 0, and from the second equation, the torque balance equation, we get F times X L minus B y times L is equal to 0. So, this is the sum over torque is 0. Now, we have from second equation, we have determined F times X L is given by 1 by 4 W naught L square. So, B y times L is equal to 1 by 4 W naught L square. Then we get B y is equal to 1 by 4 W naught L, which is half of F. And now, if you plug in the force balance equation, you get the A y is equal to half of F as well. So, now there is a take home exercise. So, there is a similar problem. Determine the, so given again a beam, now this is supported at only one end. So, this is a cantilever. So, this is given, and the external force distribution is now a sine profile. Now, given this situation, then you determine the force and the torque that is acting on the support A. So, this is a, I will leave it to you as a take home exercise. We will continue discussing on more problems in the next lecture. Thank you.